All right, example 2. So this is where I think some students will start to like this more because now you'll get to see, here's the quicker way of doing things. In my opinion, and it's the reason I designed my Desmos graph as I have, it's much easier to graph polar functions quicker if you first think of its rectangular graph. So reminder of pieces. When you look at an equation, if you're going to graph this polar is when it's r equals with a theta, I would use the rectangular form. I'm going to exchange r with a y. So the y value is equal to r. Go ahead and put that on here. The r value is equal to the y. The x value is equal to the theta. The theta will equal the x value. So I'm going to graph it. I want you to remember that the number that comes by itself is what we call the midline. The number that's all alone was the midline. So go to your graph, find 4 on the y-axis, and use your ID badge to draw, and I would recommend you use a dashed line for the midline all the way across. We got a little review here. If you don't remember, go back to lesson 3-4 and watch how to graph sine and cosine. The number in front of the cosine that's multiplying with it is what we call the amplitude. You may remember that. That was amplitude. That's how far the graph will go up and down from the midline. It's going to go 4 units up and 4 units down. Okay, question for you. Cosine. Which variable is cosine? X. So when I start at 0, is cosine at its maximum or its minimum or its midline? Cosine is x. When you start here, is there x value on the circle, on a unit circle? Is that the maximum, the minimum, or the midline for x? Max. Cosine's max is 1. So this will be 4 plus 4 times 1. What's 4 plus 4 times 1? 8. We'll begin at the maximum value, which is 8. Go over here, put a dot there. One more review question. What's the period for cosine? Perfect. The period for cosine is 2 pi, which means if you go 2 pi across, we'll have another point that's going to be at 8. You could look here in this circle. We start at the maximum at 0. We reattain the maximum at 2 pi. Okay, when will cosine achieve its minimum? Where does the minimum occur? At pi. At pi, go over here and go 4 units down from the midline. Are we good? Now, at the in-between values, that's when you actually hit the midline. So what's in between 0 and pi? Pi over 2. At pi over 2, we're going to have a midline value. And at 3 pi over 2. Now, all we're going to do is those 5 key points. We're going to graph using just those 5 key points. So on the last problem, it took forever because it was a table with all those values. I think it's much easier to use the rectangular. We're only going to use 5 values, and we're going to estimate the rest. So this, I start at 8, and by the way, what kind of shape does cosine look like? A wave. We're going to graph a wave. As best you can, graph a wave. Okay, so this is what you got to wrap your mind around when you go to graph, is how to translate it. But once you catch on, this will start to be a lot easier method. We're going to graph only the 5 key points. I'm going to start with my value of 8 at the angle of 0, which means I'm starting with my polar axis looking like an x-axis. We have a value of 8. Which way do I go if it's positive 8? Do I go to the right or to the left? To the right. 1, 2, 3, 4, 5, 6, 7, 8. What's the next key point we're going to see? Pi over 2. So go to pi over 2. And at pi over 2, what's our value? 4. So go, it's positive, so we go up 4. 1, 2, 3, 4. Put a point. Now, if you want, you can connect these two. They will be a curve, but it's going to connect from here to here. So I'm going to start to connect this as like a curve. And I'm a horrible artist, but I'm going to do the best I can. Everybody following so far? Okay, when I go all the way to pi, when I rotate to pi, as I go around, what's happening to my values as I approach pi? Well, what is my value at pi? 0. If it's a 0, that corresponds to hitting the origin. Now, don't flatline this. This was a curve, so it doesn't just hit there and make like this hard line like that. What happens to the graph is it was at 4 and it slowly decreases to 0, which means you could predict some values. Around 3 pi over 4, it looks like we're going to be a little bit greater than 1. So if you wanted to add another dot or two, go to 3 pi over 4, 3 pi over 4, and you know you're just a little bit bigger than 1. At 3 pi over 4, we're a little bit bigger than 1. It'll be somewhere in there. So this graph must look something like this. It's going to hit, and it's going to come curve through like that, and then hit the pole, which we call the origin. Okay, now what happens after pi is we're going to go to 3 pi over 2, which what's the value at 3 pi over 2? 4. So let me spin this axis. When I get to 3 pi over 2, I should be at 4. Does that mean I go up, down, left, or right? I go down. Positive is now down. So 1, 2, 3, and 4. Plot that dot. So one more time, this graph is going to go from this point, and these are all positives, so that means it's going to be going towards the angle. It's going to come around. It looks like I'm going to put the other pi over 4 point a little bit greater than 1. It looks like it's going to go and repeat the same thing, but it'll be symmetric on this side of the graph. All right, and then finally, my last point is 2 pi. What's the value at 2 pi? 8, and it's increasing the whole way, which means on this polar axis, as I rotate, it's constantly getting, larger and larger and larger as I rotate to 2 pi. Oh, man. Okay. It should constantly increase until it gets there. So it should keep getting bigger and bigger and bigger as it curves to that point. This right here takes the name of a cardioid. The reason it's a cardioid is because it's obvious in my picture. It looks like a heart. And cardio means heart. That obviously looks like a heart in my picture, correct? Okay, I was hoping y'all would say no. I was being sarcastic. It's supposed to look like a heart. I just can't draw to save my life. A heart. I said a car? Yeah. I don't know what I'm thinking about. It should look like a heart. And that's why we call it a cardioid. Cardio means heart. Cardioid is a mathematical object that looks like a heart. Let's go look at it in Desmos. The equation was 4 plus 4 cosine. You see how now it looks a little bit more like a heart? The thing it's missing is it's missing the point on this end. It's not pointed, it's rounded. But everything else looks like a heart. If you don't think it looks like much like a heart, change this to a negative sign. Change it to a negative sign, and you'll see it does look a little bit more like a heart. If I change it to 4 minus 4 sign, see, it looks a little bit more like a heart, doesn't it? What's wrong with y'all? I try to show y'all a cool lesson, and y'all you're like grumps. It doesn't look like a heart. Well, that's what they named it hundreds of years ago, and so it's sticking. You can't change the name. You're too late. Called the cardioid, which means heart, because they think it looks like a heart. All right, hey, one more time. I want you to watch my polar axis. As my polar axis spins, notice where we're plotting points. You're always plotting the point on the axis. Does that make sense? So at 7 pi over 24, if you were just starting here on your own, you would say there's 3 potential places this point could be graphed. It could be here, here, or here. The way to determine is to keep tracking along, rotating to see which one would accurately follow and keep intersecting the graph in a constant pattern. Constant might not be the right word in math because constant means flat, but in the consistent pattern. And so there's only one way of tracking it. Okay, next question for you. How long does it take to complete the whole shape? On a circle, we could complete the whole shape in pi. Do I complete the whole shape in 1 pi? How long did it take to complete this whole shape? 2 pi. Here's the reason. It's because this graph is not perfectly reflected on the x-axis. If it perfectly reflects on the x-axis, oftentimes it only takes pi to perfectly graph. I don't know if that makes sense to you, but that's how it works. Is this graph over here on the rectangular version, was it reflected on the x-axis? It was going to take all 2 pi then to see the picture. Okay, let's go look at example 3b. Hopefully we can speed it up even more. Oh yeah, we're going to keep trying to speed it up. Tell me if your equation is r equals 2 minus 5 sine theta, and you had to graph it. The way I'd recommend it is for you to do a quick sketch of the rectangular version. What could you tell me is the midline of this problem? 2. Go ahead and note that. That's the midline. So on our graph, we're going to add in a dashed line at 2. That's our midline. Okay, what does the 5 represent? The amplitude. The amplitude is always listed as a positive number, so you'd say amplitude is 5, even though it says -5, you'd say the amplitude is 5. The negative means, for the sine values, you'll do the opposite. It'll just be a transformation. So sine, when we start here, is sine at its maximum? Wait, what letter is sine again? Y. Is sine at its maximum, minimum, or midline? We start at the midline. Put that dot. We start at the midline. And remind me, what's the period of sine? So go 2 pi away, place another dot on the midline. Now sine is supposed to start increasing first, but because of this negative, sine will not increase. What will it do instead? It'll decrease. So we should get the maximum at pi over 2. That means at pi over 2, we'll actually get the minimum. At pi over 2, go down 5 units. 1, 2, 3, 4, 5. So sine goes up to its maximum. Sine returns to its midline at pi. So at pi, we have another midline point. Sine achieves its minimum at 3 pi over 2. But because of this transformation, it's not a minimum. It becomes a maximum. So at 3 pi over 2, go up 5. 1, 2, 3, 4, 5. Again, this is lesson 3-4. If later you want to go watch that video again on how to graph. Connect those dots with a wave. And let's turn this into a polar graph. All right. Tell me, what will these zeros become? It'll become intersections with the pole. This graph is going to hit the pole and intersect with it. This graph will not be perfectly symmetrical, meaning, it won't overlap itself because below the x-axis, this part of the graph does not perfectly mirror what happens above the x-axis. So we're going to have a different looking shape this time. Let's start. When we start graphing at 0, remember the r is equal to the y value. R has been replaced by y. The theta is being replaced by the x. So this is going to be our theta. When we start here at 0, with the angle of 0, our r value is 2. So place a dot at 2 right there. Now, what's happening to our graph over here? Is it increasing or decreasing? Decreasing, which means we're going to get closer and closer to the pole. We're going to hit the pole somewhere before pi over 4. So we will hit the pole. I'm not sure exactly where it'll be. I'm just going to put a dot there. What's going to happen is this graph is going to decrease. Decrease means go closer to the pole. It's going to first decrease as we spin towards pi over 4 this way. This graph is going to decrease. So it's going to decrease and hit the pole. And it's going to hit the pole somewhere around pi over 4, maybe a little bit before. And then what's going to happen? It's going to go to pi over 2. By the time we get to pi over 2, what's our value? -3. Now, negative means go towards it or away from it? Away. So we need to go down 3 units. Down 3 units, 1, 2, 3. And to make sure you see how I should graph this, follow my axis. I'm going to take it back again. We started here, and I want you to think through where the point would be on the axis. It should be decreasing on this axis. Since this is decreasing, my point should keep decreasing down this axis as I rotate it. So it moves, moves, moves. At this point, I'm at the origin, and now it's going to keep decreasing more and more and more until it hits that point. That means it gets rounded this way. Does that make sense to you? From here, it's going to keep rounding until it hits that point. So it's going to round like this, where it's getting more and more negative like that. Now, from pi over 2, we're going to increase to pi, and at pi, what's our value going to be? 2. So whenever I rotate all the way around to pi, whoops, that's not what I want to do. By the time I get all the way to pi, my value should be at, not pole, but at 2. Which right now it looks like, wait, did it go like this? Did it hit that? No. I started negative and I started increasing. So let me turn it back and show you how this is going to work. So starting here, I start at negative values, and as I rotate, it's going to climb it this way to achieve that point. So follow the axis as I rotate it. It's going to climb these values to get to positive 2. There's positive 2. I'm at negative 3. It's going to climb up this way. So from here, as I rotate this, it's going to be moving this way, this way, this way as I spin it, which means it's going to have a 0 somewhere. I don't know how I drew that. It's going to go like this. It's going to come up and over this way to 2, like that. That's how it's going to work. Now, some of you have never seen these graphs before, so you have no idea what it should look like. I kind of have an advantage. I've done this a bunch of times. I have an idea how it's going to work. Okay, so now we're there. Now, what's going to happen as we approach 3 pi over 2? My graph is going to keep increasing until I get to 7. At 3 pi over 2, I should have 7. So 1, 2, 3, 4, 5, 6, 7. Now, I should keep increasing, which means I should be on this axis as it stands. Which way should I be moving on this axis? To the left or to the right? To the left. It's going to keep increasing. That means if I follow my axis as I spin it, I should keep going further and further this way as I spin it. So my graph is going to be getting longer and longer and longer like that. It's going to curve out that in that direction. So it would look like this. It's going to curve out and hit right there. And now, finally, from 3 pi over 2, my graph will increase or decrease? Decrease until we hit 2. So it's going to decrease. So my distance from the pole, which is the R value, is going to continue to decrease until I reach that point. And this was super ugly, so I'm going to try it again. It's going to continue to decrease until I reach that value. That right there is what we call a limacon. It's a French word. Limacon means snail. People think it looked like, when they named it, they thought it looked like a snail shell. If I flip it upside the other way, a lot of students see it, and I'll show you on Desmos here in a second. That's a limacon. I call it a limacon. And the way I encourage you to remember it, a lot of you know some Spanish roots. Con means with. It comes with an inner loop, with a loop. That's how I remember limacon. You do need to know the names. If I hadn't said that, that's the first. Cardioid is heart. Limacon comes with a lima loop. That's how I recommend you remember it. But it comes from that means snail in Latin. Let's come over. In French. Sorry, in French. Let's come over here and graph it. What was our equation again? 2 minus 5 sine x. There it is. That's what the graph looks like. I told you it's called a snail. If I flip it around the other way by making it a positive 5, you see how it kind of looks like a snail shell? Some people say it looks like Toad's head. If you're a Mario fan, it looks like Toad. Yeah, Toad is a snail. No, total lie. Not true. Okay. Again, you could follow on the graph and you could see how we got our points. It's easier on this to see how with the rotating axis, what's happening with your values. But look at the axis. Remember how I said we started from 2 and we decreased first? So watch my polar axis. As I'm rotating my polar axis, you see how it's moving more and more towards the negative end of the axis? Hey, stick with me here. This is the positive end of the axis. This is the negative end. What happened at first on my graph is the graph first decreased towards its minimum. And so as I rotate, I'm going further and further down the negative end of the graph. And it's rotating, that's what gives it the curve. Until we get to this minimum. From the minimum, the graph is going to start increasing, which means on this axis, we're going to start moving towards the angle. From this point, I'm going to start moving more and more towards the angle. And so that's what happens. It continues, this point continues to move up the axis as the axis rotates. And it goes all the way until that point there. When I'm here, I'm as close to the angle as I'll ever be. And then the graph starts decreasing again. And so it starts moving further down the axis. It starts moving lower down it. That's how polar graphs work, okay? It's tricky. But once you get it, all of a sudden it'll just click and you're like, oh, I got a spinning axis and I'm either moving towards the angle or I'm moving away. And because it's spinning, it's going to curve, okay? That's how it works. All right, I have one more here before we totally switch gears. Let's do one more. What do you notice about this rectangular graph? What can you tell me about it? Midline's 5. The amplitude is 2. So let's add the midline. I go up to 5. I have a midline. This graph is a cosine. It's a negative cosine. Does cosine start at its maximum, minimum, or midline? Maximum. Because of the transformation, it's actually going to start at its minimum. Go down 2 units. 1, 2, put a dot. And tell me about the period of cosine. What is cosine's period? So if I go all the way over to 2 pi, should have this point. All right, cosine's easier to figure out in my opinion, because if these are the two maximums, the minimum should occur perfectly in the middle. When does cosine attain its minimum? On this problem though, it's not a minimum, it's actually going to be a maximum. The maximum occurs at pi. The midline occurs perfectly in the middle of those two. When does cosine hit its minimum? Not minimum, I'm sorry, midline. Pi over 2 and 3 pi over 2. At pi over 2 and 3 pi over 2. When you're graphing an AP pre-cal, all you need is 5 key points. There they are. Connect those dots. And we'll use that graph to help us draw. Will this graph intersect the origin, which is called the pole on the polar graph? Will it or will it not?
No.
It never will. Why will it never hit the intersection?
It does not touch, but
This never touches the x-axis. So this will never actually hit the origin. We start with an angle of 0 at 3. So go 3 units to the right. Put that dot. The next key point. The graph, what's it going to do? Increase or decrease? Increase. So I'm going to move up this value up until pi over 2. What am I going to have at pi over 2? 5. So go up 5. 1, 2, 3, 4, 5. We should constantly be, I say constantly, I always say, I mean consistently be increasing. Consistently be increasing up until 5. So it just kind of curves outward like that. Out because the r, the distance from the origin, it's like your radius. The radius is constantly being increased up until that point. Now what happens? We go to pi and it continues to increase. And increases to what value? So by the time I get to pi, I should be out to 7. 1, 2, 3, 4, 5, 6, 7. I'm off, but I'm going to go ahead and put the point there. So my graph should continue to increase. My radius should continue to curve outward from the pole, from the origin. Now, after we get to pi, what happens? We decrease. We basically repeat, but now we are decreasing all the way around. Goodness, it's tripping on me. So we're going to decrease all the way around. I'll put the point at 3 pi over 2, which should be 5. 1, 2, 3, 4, 5. So just decrease and try to hit those points along the way. Tell me, does this look like a circle to you?
No.
It's not a circle. Does it look like a cardioid, a heart? No. It doesn't have the inner loop, does it? But they call it a convex limacon. I'm not sure what that means in French, but they call it a convex limacon. I have no special way of thinking about that one. A convex limacon is when it doesn't have the inner loop. It never hits the origin, but it's two separate numbers. Quick hits. What was the maximum value? 7. You got those from adding. And the minimum value you get from subtracting, 3. Let's take a look so you can see it better. Graphed over here. What was our equation? 5 minus 2?
Yeah.
Cosine theta. This is called a convex limacon. And let me start at 0 here. As you can see, we never hit the pole because this graph never intersects the x-axis. Okay? But this should be a lot more consistent of an increase and decrease than what I had before. But that's what it should look like. What do we call that again? Convex limacon. So a limacon is when your two numbers are different. If the two numbers are different, it's a limacon. If the two numbers are the same, it's a cardioid. What created the heart was the two numbers being the same. Limacons when the two numbers are different. All right? With that, we have a DOL. You can try this on your own. Let me ask this. Would this hit the x-axis?
Yeah.
Yes. This would hit the x-axis or the polar. But that you can do on your own some other time. And over here, you can summarize a lot of the things I've said. A cardioid is when A and B are equal. A looped limacon, or they call it a dimpled limacon. That's the same thing as convex. That happens when A is bigger than B. So anyways, you can figure that out later. Try DOL number 5.